Okay, this is lesson 2.1, inductive reasoning and conjecture. And just a quick note on chapter 2. This is all leading up to making arguments. If you want to argue with your parents, pay attention to this chapter. If you want to become a lawyer or have good debate skills, these are basic techniques that will help you lead into the helping of making arguments. Okay, so inductive reasoning and conjecture. Inductive reasoning has to do with patterns, and so there's a little picture to help you remember patterns. A conjecture is an educated guess. Inductive reasoning is reasoning based on patterns to make a prediction on what's next. Okay, so make sure that makes it to your notes. Conjecture is an educated guess. Boy, don't in science something call that a hypothesis? It's just not fair. All these different words for the same thing. Inductive is patterns, inductive reasoning patterns. Okay, some simple picture examples. We got a pattern here. In the first piece we have one dot, then we have three dots, two along the bottom, one up here, then it increases to have three dots, then two dots, then one dot. So if we want to continue the pattern, I'm noticing now I have no instruction up here, but we're going to continue the pattern. You're going to have four along the bottom, and then you're going to have three on top of that, two, and then one. And notice how beautiful that is. So that'd be perfect. All right, that's the next picture of the pattern, inductive reasoning. Example 2, we're going to complete the pattern. This is what you'll be doing a little bit on your homework too. You're going to draw the same thing here, and then how do we determine? You have questions like this on your math minutes too. Well, it looks to me like this upper left is shaded, upper right, lower right. So it's going like in a clockwise direction. We're moving around the square. So the next one to be shaded in down here is this. And generally our pictures are not going to be color dependent. I know it's blue there, I could have done it with blue, but most of us don't have a wide variety of colors with us. Okay, example number 3. I've got 5 up here on top. These 5, and I have to pick from one of these which one's going to be next. And this one, of course, you go from easy to super complicated, it looks like. But inside each square here, this first one I have, and this is what you need to do. You need to look and actually probably say the words in your mind, especially in some of these patterns. We have a blue circle with a yellow square on the outside. Red triangle with a blue circle on the outside. Then we have a red triangle on the outside with a yellow square on the inside. Notice what's happening. I can't help but notice I said blue circle, and then I said blue circle again. I said red triangle, and then I said red triangle again. Let's test. I had a yellow square. Now the yellow square is on the outside. I have the hexagon. That moved to the outside. So now this circle, if I'm predicting right, using inductive reasoning, then this circle should be on the outside. And if I look across here, the only one on the outside is choice A. It doesn't even matter at this point what's on the inside. Okay, make a conjecture, make an educated guess about the next number based on the pattern. Okay, I'm going to suggest you either add, subtract, multiply, or divide. Since my numbers are getting bigger, it's either got to be an addition or it's got to be multiplication. It's hard to teach patterns here. You could add, but if I'm going to add 2, 8, I'm going to add 36, and yeah, 100 and something, 192. Okay, so it doesn't seem like we're going to be adding the same thing. So let's check multiplication. If I multiply by 2. Then I'm multiplying by 3. 12 times 4 is 48. And then I would take this times 5 to get 240. Oh, that seems to be kind of a pattern. Times 2, times 3, times 4, times 5. So then what would I do to figure out the next number? I would take it times 6. So I'm going to take 240 times 6. 1440 is my next number in the sequence. Okay, and I could keep continuing if I needed to from there. Make a conjecture, an educated guess, about the next number based on the pattern. Okay, actually here my numbers are getting smaller. 1/25 is much smaller than 1/4. But let's look. If my numerator, in fact I can write that as 1 over 1, is always going to be 1. So I know I'm going to have a 1 on the top. Now I'm just going to look at my denominator. 1, 4, 9, 16, 25. Okay, either add, maybe multiply. Like last we did multiply. We take it times 4, take it times, I don't know, take it times what? That doesn't come very common. But if I add just the denominators, plus 3, plus 5, plus 7, plus 9. If I add the next one, I get plus 11, which is 36. Okay? And there's another way to do this. And what I would rather that you see is these numbers are pretty special. 4, 9, 16, 25, 36. Those are all the perfect square numbers. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. So we have 1 over 36. Okay, this is a little different here. It says make a conjecture based on the given information. So in other words, you're given a piece of information and you need to like go with it. Kind of like in class when we talked about it's bisected, then your mind needs to transfer that into you have 2 congruent angles or 2 congruent segments. Okay, lines L and M are perpendicular. Which one of these 3 is going to be the next thought that you should have? You see, you're going to like use kind of an inductive reasoning here. They're perpendicular. Does that mean the lines are parallel? Well, let's think, what does that mean? Perpendicular, draw a picture, something like that. I probably can even put a right angle in there. That does not mean they're parallel. Does that mean lines L and M form right angles? If they're perpendicular, would I get right angles? And here, there are my lines. I even put a right angle in there. So I'm going to circle that, yes. Are the lines on the same plane? And most of us would probably think, yes, they would have to be. But you could have a piece of paper. Oh, am I going to try to draw this? Oh, dear. You could have a line on there, and you could have another line come down, meet at this point, and come through. Okay? So they don't necessarily have to be on the same plane. Okay, angles 3 and 4 are a linear pair. Does that mean the angles are congruent? Well, our first thought might be that they have to be congruent. But couldn't I draw a linear pair like this? And this could be, 30 degrees, and this could be 150. In which case, the angles are not congruent. If the angles are a linear pair, that's supposed to be our right angles. Angles 3 and 4 are a linear pair. Does that mean they have to be? I'm going to tell you they could be, but they do not have to be. Yeah, you're like 90 and 90, those are a linear pair. Okay, but they do not have to be. That is not an absolute there. Because right there, these are a linear pair and they're not 90. Okay, and the angles are supplementary. And I'm going to say yes to that. Your linear pair, they make a straight line, and straight lines always add up to 180 degrees. Okay, so this could be 40, this could be 140. Linear pair, supplementary. Here's a linear pair that's also supplementary. They just aren't congruent. Okay, a counterexample is a false example. Okay, it basically just proves whatever it is. So you've probably been in a situation where you, I don't want to say argued with your parents, but had a discussion with your parents, and you may have tried to prove something that they were saying is false, and you were actually giving them a counterexample. And this is one of my favorite lines to say here. An example of a counterexample. Here we got one here. All prime numbers are odd. Okay, well that seems like it's true, but isn't 2 prime? Is 2 odd? So that is a counterexample right there to this statement. Okay, all prime numbers are odd, 2 would be a counterexample. If we were in class, all geometry students love math. Usually there's somebody here that would raise their hand and say that they do not love math. And I would love to believe that every single student in my class just loves math, but it's probably not true. So we're going to say Joe Schmo, because I have nobody in here right now to raise their hand. Okay, there's got to be somebody. This person would be the counterexample. Okay, we're just going to quick discuss these. All geometry students take math first hour. A counterexample, what about my 5th hour geometry class? Those students are not taking a first hour, so that would be a counterexample. My 5th hour geometry class. And you probably have friends that are taking geometry even a different hour than that, and that they would be an example of a counterexample. If you have a cell phone, then it's a touch screen. I'm sure then not everybody has a touchscreen phone. In fact, my husband has this blue, I don't know, Nokia something or other. It's not a touchscreen, so I'm going to say blue Nokia, whatever it is. And I don't know all the names, and you might not either, but that would be an example of a counterexample. The product of an odd integer and an even integer is odd. So a counterexample, I just have to say 2 times 3 equals 6. That's an even, there's an odd. Does that come out to be odd? No, that's an even number. So this is a counterexample. The opposite of an integer is a negative integer. And most of you are like, well, the opposite of 4 would then be negative 4. And you're like, well, that's true. However, isn't negative 10 an integer? And then the opposite would be positive 10. Does that give me a negative integer? Nope. So this is a counterexample. Negative 10 would be a counterexample to this statement right here. And that's the end of the lesson.